That's amazing. Amazing. Hey everyone. Hi. It's time for the stream today. And guess who's here with me? Jan is here with me, and Jan says hi. Jan is not impressed by that. Anyways, let's do some stuff. Let's learn some stuff. What do we want to do today? First of all, hi everyone, and if you're here, in the description of this video, there's a link to Discord community. Join us. Let's work together. Let's learn together. It's really cool. It's really cool to learn together. So, what do I want to try today? We have this CPU that we just developed, that we are developing as we're going along, and it's a RISC CPU, and we're trying to follow the RISC-V kind of like instruction format. And the reason I'm trying to follow the RISC-V instruction format is so that I don't have to build like a compiler for my CPU. I don't want to build a compiler. I really don't want to build much. I don't even want to build the CPU. I just really want to understand how RISC-V CPUs are built so that I can actually debug them when I have problems with them, which happens a lot because I use a RISC-V CPU at work. But yeah, so today we're just trying to understand some more bits of this. What I would like today to do is to do store STYPE and LTYPE instructions. So STYPE is just mnemonic for store, and LTYPE is just a mnemonic for load. So let's actually look at the RISC-V card, by the way. And this RISC-V reference card, I think, let me see, where did I find it? RISC-V reference card, something like that. You can Google that, and there's like a PDF that comes up fast, and that's the one I'm using. So if you have this, you have what I have. And really what we're trying to do today is to do not the compression, not the compressed set, not the atomic set, not the floating point set. We just want the normal set for now. Yeah. So the base integer instructions for now at the moment. That's what we want to do, you know. And what I want to do today is cover some of this load type and store type. But this is going to kind of change our implementation, because our implementation so far right now only, if you look at our implementation, first of all, the first thing you notice is we only have, where's that? It's beginning to become bigger than me, so I'm forgetting. We only have a ROM section, so we only have a read-only section. But when you think about the operation of STYPE and LTYPE, which is store type and load type, you realize that we need some sort of RAM section of data. Because think about it, what does STYPE mean? STYPE is store to memory, and LTYPE is load from memory. So store, let's go down here somewhere. There's a description somewhere. So there's memory access. So there's stuff like just a moment, immediate subroutines, jumps, and calls. So there's memory access. Memory access is probably going to describe this. But yeah, like many RISC designs, RISC-V has a load store architecture. So the load store architecture is kind of what we want to try and break into right now. And a load store architecture is where we differentiate between operations that work between register and register. So whatever we have right now is all register and register. Let's look at it. Let's actually look at the code before we go on. So all of these implementations we have right now, they just work between a destination register and a source register, and maybe two source registers and a destination register. So all of the stuff we're operating on right now lives on registers. We're not operating on any data that lives in memory, you see? So what we want to do now is want to introduce some sort of functionality that helps us operate on data that exists in memory, and not rather than in registers. And that becomes implementing the load store architecture. And the load store architecture is one of the things that defines RISC-V architectures, RISC-V CPUs. Because what you're doing here is you're separating instructions between instructions that operate on memory and instructions that operate on registers. So, and this is kind of confusing because I'm saying registers and memory, and they're the same thing. And technically, yeah, they're the same thing, but not exactly. And you can assume ROM to be stuff that is compiled into your application, and then you can assume RAM to be like variables that are introduced by the thing that is using your application. So we'll think about this later. But in essence, what I'm saying here, what I'm trying to explain as I say that is I'm saying our CPU right now has no representation of random access memories. And that's a thing that I think I want us to fix. So, and introducing STYPE and LTYPE will give us that. And then the second part of the thing I want to do today is I would like to introduce these changes that I have from the test bench. So what I want to do is add some breaking tests to this test bench, and once I add this breaking test to this test bench, I should be able to have a failing test, and then I'll start with a failing test, and then I can go and what shall I say? I can go and add my code and see if my code actually makes my tests pass. If that makes any sense. That's kind of sort of what I want to do today. If anyone has any questions, you can already post them before I go on, because I'm just gonna jump into this really hard. If you have any questions, don't worry, just ask them whenever. It's really cool. I like questions, and it makes me think, and it makes me do things slower, which is actually exactly what I want to do. That's the point of all of this, is so we learn together. Okay, I believe I've explained my objective enough. So we're going to start with the test bench, and then inside the test bench we're going to write some failing tests, and then we'll go from there. So in the beginning, let's actually run the test bench. The test bench takes a lot of time, so not that much time. It just takes the same amount of time we take when we're building Zephyr. So if you have questions, this is a really good time to ask. Up your test. Let's see. Any questions? No questions so far. No questions so far. Let's run our test bench. I noticed something. Look at that. We have a warning: out of bounds L value array access ROM 15. We'll fix this. While the tests are running, let's actually go and look at that. So why is that out? Why is this out of bounds? 55. Line 15 is out of bounds. 1, 2, 3. I see. I know why. Here, this is our problem. So this is 16 registers, but because previously we would do something like this, 0 to 15, and then this would make 16 registers. But because I moved to this new linter thing, and it said, my linter advised me that if the thing starts from 0, you can just put the upper limit. And when I put in 15, I broke my code inadvertently, because this is actually supposed to be 16, so that it actually captions for 16. And as well, here, this should be 16. That should fix the thing. Because you should actually, if you see from 0 to 15, it should be 16. So there should have been 16 there. And that should fix that. Oh, sorry. I almost dropped my laptop. And as well, we have some passing tests. But let's see. We did have this warning over here, and I'm very interested in not having warnings in the builds. It's nice to have a clean build, especially this early in the test. Especially this early in the development cycle, it would be good to have something that just builds clean. Yeah, I don't see the warning anymore. It seems like we've fixed that. Okay, so cool. Let's jump into writing some tests. So we're not gonna see this until probably the end of the session, likely. So let's start from here. I think the first thing I want to adjust, if I remember correctly, is so the way we are going to test this Let's see, can we do that? Can we do that? Just a minute. Okay. 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 And then I want to go here, and then I want to A. Okay, cool. So that we can jump in between easily. The first thing I want to do is I want to realize here we have like our ROM has like 16 instructions, and we have this first 5 occupied by the tests that we're doing right now, and I would like to add maybe another 4 or something, or 5 or something. I don't know how many instructions it will take to test what we're doing. So the first thing I want to do is allow my test bench to actually go further into the instruction set, and I think I can do that here. So this is the first place. I'm gonna make this 20. That way we can actually process as many results as many more instructions than the 10 in case the tests pass through the 10. So the thing I will start with is something like, I think I want to add, like, shall we do something like load something into some memory? How do we do it? Let's put something in memory, so add some immediates. Yeah. Let's put something in memory, add some immediates, and then after we put it in memory, we can load it, or we can I have the thing. Take some bit of data and load it, add some immediate instructions on it, and then what we do is we store it to some sort of memory. So we do an STYPE, and then after we store it into some STYPE, we can load it again. Yeah. This makes no sense, but you'll see. So I'm imagining on how to test this. And if I need to, the easiest way is to store something that I know. So put it in memory. I know exactly what it is, and then to load it. And then if the thing I load is the same as the thing I store into memory that was blank before, then I sort of have it. It sort of works. If that makes any sort of sense to you guys. So we can start with like some random number. Let's actually go here. Let's add some instructions here. Yeah, this is 5 plus 3 should be 8. This is the wrong comment here, so this is confusing. So yeah, let's add some test LTYPE, and STYPE. Here. So bear with me. I'm not very good at this, and I'm just sort of like figuring out my way as I am going. So I'll actually just, can I copy this? Y. I think that's and then my thing doesn't like it when I have spaces. So the first thing I want to do is I want to go like x1. Let's put something in x1. Yeah, let's put something in x1. So x1 should be something like, I won't use the same thing. Let's do something like the answer of life is 42, and then so I'm gonna do like a add immediate. So if I do an add immediate, I will if I do an add immediate, then and if I'm going to add immediate, I'm going to add it to like so this is after SW LW. So after load word, after store word, and then LW, it should be 42. So and this should actually check, because I'm using X1, I want to use R1 here. And yeah. So that's the first part. And then the next thing, but this is just the way. Okay, so let's kind of go back. It's nice. It's easier to just jump through the stuff as we do it. The way S-type and L-type works is that in S-type you have this immediate 0, 5. This is going to be like the pointer to the base of the memory, and then you're going to along with that you're going to be able to how do I say it? You need to use an offset. So you can point to, like, here we'll have a bunch of RAM. We have a bunch of RAM, 64 KB of RAM. And then we say, in this RAM, give me data. Give me the word that lives on offset something. Okay? And that should actually give you, you can have, like, let's assume you have like the mem slabs we're doing in the other side. Let's assume you have like a 64-bit thing and it's holding all your RAM. It's usually on my STM32F4 is something like 192 kilobytes. So 192 KB thing that holds all your RAM. So you know the address of the beginning of RAM, and if you want to put, because it's random Excalibur. Let's reason through this together. So let's actually take a pencil. So you have like a bit of RAM like this, and this is your RAM. So this is your RAM. This is our RAM. This is my RAM. Okay, and in this RAM we have like these slots, and these slots are like, say, each 32-bit. 32-bit. Okay, and then all of these are words that we want. But the way you will use your RAM is you'll put something in here, and then you'll put something in there, and then you'll there'll be like all these other contiguous sections over here, and then you'll put something in here, and then something in here, and then this will last this much. But that's just, you can put something randomly everywhere. And the way you're going to do it is that way, because in case you need to modify this and rewrite it, it might expand. So sometimes you can give it space. You're going to do some sort of like scatter buffer technique. I don't know if you know. It's almost like scatter buffers. You're gonna do some sort of like scatter buffer technique where scatter buffers. Where is it? Yeah. So it's kind of like stuff is everywhere, and you give stuff space to expand on either side because it might be edited. Anyways, while that comes. So if this is our RAM, we will always have the address to the beginning of RAM. This is the address of RAM. This is the RAM address. Whatever. This is the RAM address. But whenever we want to access this thing, since we only have this, we're going to use some sort of offset. We're going to say, go 3 blocks into the RAM, and give me the 32-bit thing that is there. Give me the word that is there. You see? And that's where this parts of the so this immediate gives you like it gives you the address, and then you're going to this is going to show where the RAM starts, and then you're going to add an offset to it, and that offset is going to give you the location of the actual thing. It's easier to do than to explain somehow. Okay, cool. So first of all, we put something there, and then the next thing we want to do is we want to check that the base address of the thing is 0. So display, this is something like x2, I think. We can use x2 here, x2 again, and then this is do base address should be 0. Because remember, this is before we have done anything with it. So it should be 0. Like this is, that's why we're writing the test, ut dot, and then here it's going to be R2. I mean, this, we can choose them as we wish, but This is what I'm using for now. So this is now going to be the base address of the RAM memory you're going to reach into. And then the next thing we're going to do, I think what we want to do now is we want to, you remember that 42 we put in R1, we should want to load it up. Okay, and I think we want to put it in X3 if I'm not wrong. So yeah, so because we're just doing register stuff. So load value here should be 42. B42, which is, it's gonna be in hex. It's going to be in hex. So this is 2A in hex. 2A hex. 2A. So that it makes it easier to actually write the assertion data and just write all the assumptions in here. I mean, I know I'm doing all of this quite wrong, because every time I go and I get this reviewed by people who know Verilog at work, it's like they show me things that I didn't know. But the point here is to just sort of like try, and if it doesn't work, it's fine. If it doesn't work, just try and see what happens, because what I'm doing here is just building the intuition for like, this is how it works. Then the next time it breaks for me, I know what to go and check. So this should now be a copy of X3 because we loaded it. So we stored it, and then we loaded it. And when we loaded it, it should be the same thing we stored. And if this actually succeeds, then we've actually implement should be 2A for 2. And I think we can do it like that. And no, this is just a display, and then this is just a H, and then this is that, and then DUT, and then this is DUT should be R4. Okay, easy. So this is just like all of this. This is not exactly our. These are not our assertions. This is just stuff that we can observe that makes it easier to see. The assertions themselves are these things. This one's down here, and this is actually one of the bits of advice I have gotten from work. If possible, I should move this into assertions, actual assertions, not just ifs. And the way to do that, as I was reading earlier, is here. The way to do that is, if I wanted to do this as an assertion, I would do it this way. But my streams I do this thing where I discover something and I want to do it, and then it just takes my stream in a very... Should we do that? Should we do that? Because what else is the reason? What else? Why should we not do this? Why should we not do this? Let's try with one and see what happens. So let's look at it. Assert this, and then this is a triple equal, so it should be okay. So here I can go assert, and then if not equals, so this assert dt I, this should be da, okay? And then that should just give us that. And then if it's not that, else begin. This is okay. This is okay. This is okay. This is okay. This is fine. So else begin, and then and now I'm officially in code blocks. So I want to go here, and then I can actually leave it like that because I think that should work. But they're doing theirs in one line. And if I do that, I need to do error count here. I want to do plus plus of the error count, which is fine, which is the thing I'm doing below. And then if that doesn't work, I would like to, rather than display, I would like to do error here. Error here. I'm very scared of running this. The reason I'm scared of running this is because I have this thing where I do tangents, and then if I do the tangent, and I have no, personally, I have no problem. It's the whole point of why I do this. The thing is, when I do that, the stream title does not match what I actually end up doing, and I'm embarrassed about that. I don't know if I should be, but I am. Cheers. Cheers. Thank you, my linter. It seems like you think that is valid. Let's actually run some tests, and we will handle a couple of questions now. Okay, while that is building, does anyone have any questions? No questions? No questions so far. Okay, let's see. Let's see if it works. Let's see if something happens. Any questions so far? If you got lost, if I got lost, is it hung? I don't think it's hung. It's actually slower than you think, so I don't think it's hung. The tests take long, and the reason the tests take long is because we run a very slow clock cycle, which we can adjust for testing. Let's do it for testing. Let us do it for testing. Let us adjust the slow clock. But the moment we adjust this clock for testing, it will mean we will not be able to we will not be able to observe the LEDs. Clear. Okay, let me do this now. Up here. Clear. Somehow I destroyed the state of my up here test. Let's see. This should now go like much faster. It should just explode quickly. Boom. There you go. There you go. It worked. It worked. So we can actually move all our code to that. And remind me to always test in. Okay, I can just do it. Let's quickly throw in that because I really like that. I really like that one, that new one. A sat, and then in here it should be a begin. This should be a begin, and then this should be an else here, and then this should be an error. This should be an error, and then this should go before this, and then this should go like error. Sorry. Anyways, error count plus plus. Okay, it doesn't like the space here. I can't leave a space here. I don't know why my linter does not like that. And then instead, I'll do this. I'll remove this, and then this can go here. This is the same thing. And then this assert as well. And then in here, I don't think I have a space there. I can go here, and then I can say else begin. And then in here, I can actually move this up there. Error count. We will make this fail just now, and it will work gloriously. However way you want to hear that. Okay, cool. So this is good. This should now actually. This means we are in assertions. So I kind of took a tangent, but we still managed to stay in the place we want to be. So let's actually add some failing tests now. So we want to add these 3 failing tests here. You see, they're not 42. They're not 42. This is 2. This is 3. So this is actually wrong. So cool. So assert. This should be. Now, since we're testing this, I think we can just go with the same thing. we can just use the same registers we're using. So we should just go with the way we're going from up here. So could I just copy this? 1 2 3 4. Could I just copy and change the assertions there? Yeah, I could go. I could. Yeah. Why? Just a moment. I can actually just come here and do, I think, not two. Just, yeah. Okay, cool. So now, after we do this, this should be assert, this should be not H5, this should be, it should be H2A, not 2. This should be 2A. 2A. Yeah. X1 should be 2A, should be 2A stroke 42. Got whatever. And then this one should be 0 if I'm not, this should be 0 because we're not using any offset right now. Should be 0. Got, yeah. And then this one should be what should be in 3? In 3 should be a copy of 42 again. So here it should be 2A as well. H2A. So this is 42 here. 42. 2A. Yeah. And then I want to kind of take this first one and take the fourth one as well. And then why? I wish to learn how to implement what is it called? I wish to learn how to implement delays, because once I learn how to implement delays, I'll show you. This should also be 42. Okay, cool. Once I learn how to implement delays, we can run these LEDs on delays. Rather than running a slow clock in the whole CPU. Then we can just let the CPU run as fast as it can. But I haven't learned that yet, so it's fine. Let's see. Will our tests actually work? I see. So I just need to run up here test. Something of sort. No, that's wrong. Our assertions are wrong. So our assertions are wrong. This is where I don't know how to use it correctly. Should be 2A got H, should be 2A got this, should be this, should be this, should be this. Should be 3. Where? Error X1 should be 5, got 5. Wrong. You shouldn't. Got 5, but should be this. I mean, I also have R4, so we're using here R5 all the way to 5. I can use 6 to 10. We can actually just go with 6 to 10. Let's actually do that. That's easier. 6, 7, 8, 9. That way, 6. That way, we don't have this repetition. I mean, at some point we will have to learn how to even just use one register and just cycle through it, and so that's okay, you can do that. That's okay, you can do that. What do I want to do here? That's fine. That's okay. So, and then I want to go back here, and instead of whether the HO, this is an error, and then do I need an error? No, I do not need an error. So I don't need it to say error. So actually, let's start with the new test I added. Sorry. So let's that's okay. This is 5, this is 3, this is 8. That's fine. Those are the ones I checked before. So now I want to check here, and I want to check R6, and here I want to check no, it's you. I'm sorry. So I don't need these errors. Okay, cool. Let's clean up the code. This is the thing I was saying about like adding. Whenever I do this in my thing, it just becomes something of its own. Yeah, that's fine. Yeah, this shouldn't be 1. This should be 6. And then this should be 7. And then here I should actually yeah, so actually that as well should just change to x6, and that should be 6, and then this should change to x7, and that should be 7. I just want to avoid that little place where I get, it should be 8, and then this should be 8, and then this should be 8. But in essence, our test already failed, so we've already won. I just want to make it clearer because it's just easier that way. This is 9, and this as well is 9, and this as well should be 9, and we do not need an error here. Let's see what happens when we do that. So, okay, cool. X8 and 9 are not set. X1 should be 5, got 5, that's wrong. TB 70. Number 70. Okay, number 70, 67. R1 should be 35, should be should be 5. Why is it wrong to be that? But it's 5, yeah, should be 5. X2 should be 3. Somehow, you see this assertions, do you remember the assertions? This was an if, this was going backwards. So let's actually just do that. That's wrong. So okay, cool. Yeah. Let's see. This might actually just make everything perfect. Amazing. So we have a problem. This XXX, this is not a good thing. This means it's not set up. It shouldn't be that. And how come we only get 3 assertions, not 4? Something is wrong as well. 9, yeah. 6, 7. Else begin. we get 4, we get 3 fails, 4 errors, but x7 should be 0, God said that. Why is x7 not becoming an error? x7 should be 0. Aha! Error. Perfectly amazing, perfectly amazing. Amazing, this is good. This should not be XXX, this should be zeros, or should be something. Actually, it can be XXX. The reason it's XXX, it means it was never instantiated. But let's actually see if this they get instantiated somewhere, and actually if that's the case. No, nothing. And I should probably add them here. Or let's save that. We probably should write a comment. Let's see in here. Do I actually do any sort of non-zeroing? But we do zero everything. So yeah, we do zero everything. So it doesn't really matter. Everything is fine. Everything is zero. And I think the reason they're X's is because we're touching registers that are not operated on at all right now. And because they're not operated on, it just ends up breaking. Cool. Any questions so far? I'm going to stop for questions. Any questions so far? Anyone with questions? No questions. Cool. Let's write a comment. Let's write a comment. Maybe there's something on Discord and I haven't checked. Oh yeah, I'll see that later. No. Yeah, let's write a comment. Git status, git add tiny CPU TV git diff -- staged. I think so. We moved to assertions and we added test for LTYPE and STYPE. Okay, git commit -v. Assertions move to assert in test match. Test for basic S-type and L-type. Yeah, that's fine. Git check out PR add SL type. That's a weird name for a branch, if you ask me. Okay. Cool. Git log. We're on a new branch. We're on a new commit. Okay. So now, let's actually think about this. Then we need to add, the first thing we need to add is, because remember the thing I started with. Our current application can't really handle S-type and L-type. And the reason for that is that we do not have an allowance to add, we do not have RAM memory. So the first thing we probably need to add to our application is, as well as our ROM, we need to add some RAM memory. Let's add 255 bytes. What is a 32-bit word? What is 32 bits? Is it a double word? Okay, whatever. 30. No, I don't know. It's a word. Okay, so let's actually just call them words. So let's add 255 words of RAM. Okay, RAM memory 255 watts. And right today we're only just gonna do like load word and store word. We're not gonna actually work on we're not actually going to work on how do I say this, half word. You know, there's I should stop remembering stuff. You see, S-type, you can do a byte, a half word, a word, a load byte, a load half. You can do this. So I think what we're gonna do is a store word today, a store word and a load word. Just that. Just keep it simple. Recognize what is going on, so that we understand what is happening, and then we can go from there on. We can kind of like go through that. Now I have to think about how to actually. So first thing we need to do, let's add some memory location. So let's do a reg, and then I want to do reg. I think I'll just put it here, and then I'll make the app do it itself 310, and then I'll call this RAM. I want to call this RAM, and then I want to call it. I want to say go from. So it's. I want to say 256. 256. 256. Yeah. So I want to do that. Let's add some RAM of 256 watts of RAM. So let's say 256 watts of RAM. Okay, and then the other thing I want to add, so you see we have an immediate S, immediate I. The immediate for I and the immediate for the immediate type for S, for register types, is different for the store types. So we need to account for that, and that one was a discovery in the hardware. So you see, immediate here for register it's this, but for store type, immediate is that and that. I don't know if we're gonna use that right now, but this is the one we want to use so far. So we need to add this. We need to add this sort of structure for the same way we do it here. The same way that way it's easier to like access. So this we need to do this, but for immediate for the S. S and L is the same thing because they do load and store is kind of the same family of. They might be separated, but they're the same family of instructions. So let's do a wire sign. It's going to actually look quite the same, and then this one's going to be 310, and then this I'm going to call it IMS. Okay, and then here instead of going for the shall I do the 20? Shall I make the sign 20? Yeah. So we can do 20. This is just to make the sign IR, and then this is 31. And then but this one will be a little different in that in here this is a concatenation. So you're joining things to represent a 32-bit. So here we're joining this first 11 or something bits, if I remember right. So we're joining this, you're joining this and the rest of the stuff. So this immediate and the rest of the stuff to make up this is a concatenation, sorry. This is a concatenation. So the thing we want to do for our one is we want to follow the new one, and this is going to be IR. I think it's going to be something like 20, 25, 31. Okay. 31. This is now to 25. That's the range. 25. I might be wrong. Yes. And then in here we want to add another one at there's another one. There's this one. You see an 11.7. So that's like 1, 2, 3, 4, 5, 6, 7. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I just figured it out. This was very confusing before. So there's 12 bits for the immediate here. The 12 bits go like something like 11, and then they make a sign. So you make you concatenate them so that you can make a sign. And this is because whenever we do these types of instructions, we will scale the data in such a way that we will lose some of the data. So you want to maintain a long amount of sign so that you don't lose it when you scale it the stuff. So this is just the same as this. It's just that here it's spread between two sections of the register rather than here it's in one like contiguous. It's a scatter buffer already. It is. Scatter buffer. It is, because this and this is the same piece of data, but you have them living in two different places. So let's actually do that. This is 7 to 11, or rather 11 to 7. So here we're going to add, I think IR, and then we're going to say 11, 7. I think that should work, and then that gives us our immediate store type register, basically. And then let's actually do some more stuff here. So this needs to change. We need to go like, let's actually use the ones we know already. So let's add immediate, rather than x, let's say x6, x0. Shall we use x6, x0? Yeah, cool. And then this should be like something like 42, okay? And then let's put an offset here. Let's put no offset here. So it just like, because we're doing a word, so this is x7, and this should be 0. x7, x0, and then this should be 0. And then, okay, cool. And then the next thing we want to do here is, so we've added a 0 offset, and we've loaded 42. And then that's the first thing we want to do is store SW. SW here should be x1, x6, okay? Store x6 into offset 0. Yeah, so 0, something like 42. Easy? Or rather x2. Not x2. Not x2. I want to use, I used x6, x7, x8. Yeah. And then x8 here will hold our destination RAM address. Yeah. And then here we'll add, the next thing we want to do is load word. And then in here we want to load the word into, what's our test doing? We want to load the word into x6, x7, and then we want to load the word into, is it x8. Let's load the word into x8, and then when we load the word into x8, this should be 0, 0, x8. What am I doing here? And then I do my assertion. Okay. And then in here, let's do an or immediate. Or immediate. And this should be x4, x3. So this is x9. Or this should actually just give us a 0. But now I have to figure out how to write these instructions in hex. Yeah, you can remove it. So we can actually figure out quite a lot. Let's actually just go here first of all. Add x42. So this one is going to be 42. So this is going to be 0, 0, 0, 0 instead of, and then here it's going to be 2a, 0, 2a. 2a. I think so. And then this part is, this one can be quite zeros all the way to the end, but I need to point at this is insane because it's easier, it's always so hard. I don't know how to write binary. So just a moment. What if I just reuse my registers here? So let's just 1, 2, 3, 4, and then and then in here I should also just do 1, 2, 3, 4 when I get back to testing them, because I don't want to go figure out. I remember it took me a while to figure out how to write those things, and I don't want to go figure it out right now again. It's just, it's almost already time, so it's fine. I want to maintain this sort of like ongoing context, and it's easier for me because I'm doing a lot of stuff. Up here, test. It's checking the wrong ones. Cool. Okay, cool. Yeah, that's okay. So far we want to and this is an error. Okay, and then verify, and then I want to do 1, 2, 3, and then when you see 1 again, just put a sign here, and then let's do STYPE and LTYPE, and then here, and then basically here I want to do, rather than do that, I want to do 1, 2, 3, 4, 5, and then this is gonna be 1. This is gonna be 1, and then this is gonna be 2, and then this is gonna be 3, and then this is gonna be 4. If I'm not wrong. And if I run these tests, amazing. This now works. Now we can move a little bit faster. So the reason I did that is so that we can come here and we can do this now. So now instead of going and figuring out a new instruction in here, we can just do I, and we can just follow the first instructions, which is 9, 3. Okay, cool. And then in here we can go 0, 0, 0, 0, but we can follow the second instruction, and then we can just use the second result is 1, 1, 3, and then here and the next one, instead here we can go because now we're using 1, 1, 3. So do I need to do something like this is, how do I count to 6? 0, 0, 0, 1, 1. Is that how I count to 6? 0, 0, 1, 1. So 1, 1. I, please. 1, 1. Something like that? Something like that. And then, so this is gonna be actually wrong. This is 1, this is 2, this is now 1 again, this is now 3, and this is 4. Okay. So So this one works, these two work. And then this is load 8, which is 8 0 0 1 1, and then 2 0 2 3 2 0 2 3 2 3. Okay. And then to actually load the third one is 0 0 1, and then it's gonna be 0, it's gonna be 0 0 all the way to 1 here, and then it's going to be 1 2 1, but this one's gonna disappear, and then the last 3 is going to be 8 3. And then to OR this, I can just OR them the way I have the OR up there, and then but I'll be using I'll be using different addresses, so I can just go 0 0 0, and then 1E 1E, and then I hope I get used to this. I should learn how to count in hex. 2 1 3, something like that. Something like that. Let me check for questions so far. No questions. Okay, cool. Let's actually test that. We never run those instructions, so basically that's actually what happens. Let me just do that here. So this is R type, and then this is going to be I type. So what we now need to do is add 2 more here, 2 more down here. After this default. Wait. So default and last return register, and here. So this is where we need to add them. So we need to add here. We need to add S type, and then after that we need to do L type. Okay. So how does this work? How does this work? Let's actually see. So to store this here, what we want to do is this. It's actually here already. I have the card. So I just need to check. Number one, I need to check for this. Store type. Where is store type? I need to check for that opcode, and to load, I need to check for that opcode. So that's fine. So let's actually check for those 2 opcodes. And I think here we're gonna do something like 7. S type, let's just copy it, this opcode, copy, I think that's the one, S7, and then that, and then we're gonna do, actually yeah, this needs to be a binary, and then we're gonna do a begin, and then we're gonna do an end. That's cool. So that sorts out S type, and then for L type, we want to do that. Copy. For L type, we want to do 7B, and then that, and then begin and end. And that actually just begins to sort it out for us. That actually puts some sort of implementation. Let's see. Can we make it at least fail or something? Case, and then we want to do B, case binary 0 1 0 0 1 0. Case B 0 1 0. Case binary 0 1 0. No. That's here actually. We want to check funct3 because S-type and them, they have funct3 and funct. Yeah, they do have funct3 here. So we want to use funct3. This is funct3. So we want to check funct3. So here I want to do case funct3 in here, and then we want to do default, and then we want to do that. that, and then we want to do end case, and then that's going to be that. That's okay. And then the same thing we want to do here. Anyways, let's just add the, so the instructions we want to do here, the instruction we want to do check for here at 0, 1, 0, and that comes from here. Load word to 0, 1, 0. Okay, so that's what we want to check for. So 0, 1, 0. In case we have 0, 1, 0, we should read from 0, 1, 0. We should read from R. We should read to our destination, or rather even from our destination, and then we should go like RAM, and then in RAM we should reach into RAM and get RS1, this address. Okay, and then in here we should add it to I. That way we've kind of like loaded word. So this gives us a load word. This gives us okay, I did it wrong. L. So this actually gives us a load word. Load word. Okay, so and that gives us a default, and then if I do that, that should give us something nice. And then in here, let's come and do the same thing so that we actually get the muscle memory for it. And then in here, we want to do func3, and then we actually want to do the default, and then the default, I want to do that, and then I want to do that, and I want to do end case. If I save it, it formats it for me, and that's actually good. And then we want to do load word. We've just done a load word. We want to do a store word, which is also 0 cross 0, 1, 1, 0, 1, 0. So 3, and then binary 0, 1, 0, 0, 1, 0. And then in here we want to RD, yeah. It's gonna that, and then we're gonna say this is going to come from now this is now storing the word, so it's gonna go actually opposite RAM, and then RAM we're going to do RAM into RAM, reach into RAM and give me reach into RAM and take R into RS1 into R source 1, reach into RAM and do that, and then that, and then give it the offset we want to get, which is I'm S, not I'm S. Reach into this address in RAM, and then from that address in RAM, set this address in RAM as RS2. That's really it. That's really it. And then this goes SW. What did we just do there? So if you think about it, let's just actually look at it. So this is S-type. S-type. Okay. We're gonna be done soon. It's already 11:30, but I was just so close to finishing this that I wanted to do it. So what is happening here? In LTYPE, we check func3, which is the thing that gives us the opcode, which gives us the operation that should be done. They extend the opcode to specify the operation to be done. So right now we're just doing IM add. We check func3, and in case func3 is 0 cross 1, 0 cross 2, which is here, func3, load word. Are we looking at load type? This is 0, 2. And then because of that, we just do this. That's all we do. Memory, we set the memory, we set this into memory. RD is this from memory. And then in store, with that, we say this location in memory should be set to RS2. That's really it. I don't think our tests are going to pass. I genuinely think they're going to fail. And also, I want to keep this tradition we have. Let's keep it for a while so that we can also test with do I really want this to go on? Nah, we need to actually start removing that LED stuff from our CPU. We probably need this. Actually should give us some module on the side where we do LED stuff in there, and that actually gives us an opportunity to learn how to cut out our modules differently. Let's actually just try and up your test. Yeah, it's just 15 minutes and then I'll feed you. This is kind of, it's changed, but it's not where we want it to be. So let's actually go back and look at our code. Let's go back and perhaps actually before we do that, let's look at this. This is X. Well, which one's the facing X6, X7, X9? Okay, cool. But this should be X1s. This is sort of what I was. Okay, so X1. This is also X2. This is also X4, X3, and X4. I don't know why it stopped. Okay, this is what we're gonna do. We're gonna push broken code for today and go figure out. There's something we need to figure out with addressing so that it works out. That's really it. There's something we need to figure out with addressing so that it works. It's not using the addresses the way I want them to use them. So as you can see, the new CPU instructions are not being followed. Somehow our new instructions, these two new instructions, they're not being actually implemented. So this 0, 1, 0, 0 and 0, 0, 1, that's sort of they look the same. Load is that and S is that. Load word 0 cross 2 and load store word 0 cross 2. Somehow we are not actually even running those. My code seems to never actually run. My code seems to never actually run these options in here. That's actually what I'm seeing, because what is happening is case func 3, case func 3, and there's that. So it's likely the issue is likely in here in the way I was writing my instructions. The issue is likely in here, and this is probably what I need to go and learn how to do. So H0280033 9093, and that should work. That says 42. Add 42 to a place, but these ones work, so I don't know why they don't work. Unless okay, cool. Just a moment. Baba, you can't be up here. I'm sorry. There should be something here that actually might give us stuff. This gives us 20, and that actually runs 20 cycles plus 1, waits for the slow clock. It's as though it only runs the first few instructions and then it never runs the next ones, because we never really The other thing I could do is figure out how to write instructions for the longer parts. Anyways, let's stop there. This is not going further. Git status add git add tiny cpu.v git add tiny cpu.tv git diff dash staged. What's that? So there's all of that. We went to 16, we went to 56 words. We did that right. We concatenated that right, and then that should be okay. So that's fine. That's okay. So, but it's okay. And then we're only going for 2, and then we added this new instructions. Okay, cool. Git commit LTYPE implement basic IType and SType and LType opcodes. That's LType. Okay. Git push, and this should give me this, and there should be a git push dash set upstream origin pr add sltype. Yeah, cool. Okay, the code is up. I'm going to think a little bit. I bet you we're doing a very silly mistake somewhere here in our instruction set, because that's actually the thing I'm not good at. I don't know how to write those instructions properly, and most of this was kind of like trying to guess, and I'm trying to just join all the instructions that I had before and use them here, and I'm going to see if I can kind of figure out what the problem is. It should be rather straightforward, to be honest. I think it's going to be straightforward. And once I figure it out, I will post and we can go forward with that. Okay. Cheers everyone. Thank you. In case you have any questions, you can ask. Does anyone have any questions right now? Does anyone have any questions? Cool. No questions so far. Cheers. Thank you for joining for this session. See you next time.